Good morning, everyone. Welcome to Arkajan online program. Today we are going to start a course, Computer Fundamental and Organization, in which we are going to study Module 5, that is Computer Memory. Computer memory, a computer is an electronic device that takes raw data as input and processes it, then provides the desired result. It has the potential to execute programmed computations quickly and with great accuracy. Put in another way, the computer receives input such as data and stores it together with instructions in memory. Use them when required. The data is then processed and converted into valuable information. After that, it provides the result according to the inputs. Here, input means the unprocessed data that we want the machine to handle and then give us a response. And output refers to the outcome of the machine's processing of the unprocessed data, which may include data analysis, searching, distributing, sorting, and more. Consequently, a computer is also referred to as a data processing system. What is memory? A computer memory holds the data and instructions need to process raw data and produce output. It is the same as the human mind, where data, information, and instructions are stored. It is a data storage device or a data storage component where instructions for processing data are kept along with the data that has to be processed. Both the input and the output can be held here. The computer memory is divided into large number of small parts known as cells. Each cell has a unique addresses, which mean varies from 0 to memory size -1. Computer memory is of two types, volatile RAM and non-volatile ROM. The secondary memory hard disk is referred as storage, not memory. Now, next we have characteristics of main memory. It serves as the computer main memory. As compared to secondary memory, it is faster computer memory. Typically, it is a volatile memory. Without primary memory, a computer cannot run. These memories are semiconductors. But if we categorize memory on the behalf of space or location, it is of four types. These four types on behalf of space or location are register memory, cache memory, primary memory, secondary memory. Basic of computer memory hierarchy. The main component of every computer is a memory hierarchy, a layer from that classifies memory based on access to speed, potential, and expenses. This hierarchy typically consists of registers, cache, RAM, and storage device, which incorporate HDDs and SSDs. Register. Registers are the fastest and smallest figure of memory. Residing inside the CPU, central processing unit, they keep the fact that the CPU is actively used or manipulated. Registers provide the fastest feasible way to get entry to store data. However, their limited capacity means they are capable of saving a small amount of data. Cache memory. Cache memory is the mediator between register and RAM. It's quicker than RAM but larger than register. The CPU uses cache memory to save often excess data and instructions, decreasing the time it takes to fetch data from the slower RAM. RAM, random access memory. RAM is the volatile memory. It allows for rapid read-write operations. However, its content material is erased when the computer is powered off. RAM is vital for multitasking, allowing speedy switching among various applications. Storage device. Beyond RAM, we encounter storage devices like hard drives and solid country drives. These provide non-volatile memory, retaining facts even if the power goes off. While storage devices have big capacities in terms of RAM, they need to be faster in terms of information access. Next, we have how does computer memory work? A program is loaded from secondary memory to primary memory. When it is opened, there are several types of memory and storage. For example, a program being moved from a solid state drive to RAM. The opened software will be able to communicate with the computer processor at a faster rate because primary storage is accessed more quickly. The main or primary memory can be accessed quickly from storage location such as temporary memory slots. Data in memory is only saved temporarily since memory is well volatile. Data saved in volatile memory will be erased immediately whenever the computer is turned off. A file is transported to secondary memory for permanently storage when it is saved. There are numerous kinds of memory present in the computer. Depending on the primary memory utilized, it will perform differently. But semiconductor-based memory is typically connected with memory. Integrated circuits utilizing metal oxide semiconductor transistors based on silicon will be used to make semiconductor memory. Function of computer memory. Function of computer memories include some of these types. Data storage. The primary role of computer memory is to keep data. These includes the OS, operating system, software packages, and user-generated documents. The hierarchical agreement guarantees that the most regularly accessed data is stored in the fastest, smallest sort of memory. Program execution. When software is launched, it's loaded into RAM for execution. The CPU fetches commands and facts from RAM and the quicker cache memory. When possible, performs the critical computation. The rate and overall performance of this approach impact the overall performance of the PC. Temporary storage. Memory is used for brief storage of records throughout ongoing operations. For example, at the same time as you edit a document, the adjustments are quickly saved in RAM until you save the file. This temporary storage is crucial for seamless individual considerations. Caching. Cache memory performs a pivotal function in caching regularly accessed information. By preserving a copy of these records near the CPU, cache memory reduces the time needed to retrieve information, enhancing the overall speed of the system. Virtual memory. Computer structures use a concept known as virtual memory to simulate large RAM capacities than are physically available. This includes the use of a part of RAM, while virtual memory allow the execution of large applications. It's slower than physical RAM. Types of computer memory. In general, memory can be classified into primary and secondary memory. However, even when just talking about primary memory, there are many different types of memory. There are some examples of primary memory such as follows. Cache memory. The cache, also known as temporary storage area, is more readily available to the processor as compared to the main memory source of the computer system. It is mounted on different chip that connects to the CPU via a bus or it's frequently built directly into the CPU chip. Hence, it is also known as CPU memory. RAM, the term RAM refers to the fact that the processor can directly access any storage location. Random access memory or RAM is a piece of hardware that serves as the internal memory of the CPU. It is often found on the computer motherboard of a computer. When the computer is turned on, it enables the CPU to store programs, information, and results of the program. Also, it is a computer read-write memory, which means data can be added to it as well as read from it. Dynamic RAM, a type of random access memory that is used in computing system, primarily PCs, is called dynamic random access memory, DRAM. The data or program code required for a computer processor to operate is often stored in DRAM, which is a kind of semiconductor memory. Each piece of data is stored in DRAM in its own passive electrical component, which is located inside which is located inside an integrated circuit board. Each electrical component has two value states known as zeros and ones in one bit. Static RAM. As long as RAM or static RAM receives power, it keeps data bit in its memory. It does not need to be refreshed on a regular basis. In contrast to DRAM, which stores bit in cells made up of a capacitor and transistor. Double data RAM SD RAM. Theoretically, DDR SR RAM, that means double data rate SDRAM can increase the memory clock speed at or to at least 200 megahertz. It is an SDRAM. Double data rate for synchronous dynamic RAM. DDR4 RAM is the successor to its predecessing DDR2 and DDR3 iterations. It is a kind of DRAM that contains a high bandwidth interface. Higher module density and lower voltage requirements are both possible with DDRAM. It enables dual inline memory modules, DIMMs, up to 64 gigabits. Also, higher data rate transfer speeds are paired with the Rambus Dynamic RAM, a memory component called DRDRAM made a guarantee to transport up to 1.6 billion bits per second. The RAM controlled subsystem consists of RAM, a bus connecting RAM to the microprocessor, and a computer using device that make up the system. Read-only memory ROM. ROM is often only read from and not write written to, which is a type of computer storage. It is non-volatile in nature, which means it stores data permanently. The programming code is stored in the ROM that enables a computer system to boot up or regenerate every time when it is turned on. Programmable ROM. PROM is ROM that a user can modify only once using a unique device known as PROM programmer enable a user to customize a microcode program. Erasable PROM is a type of computer memory that can be erased and reused. It is a programmable read-only memory PROM. Electrically erasable PROM. A user modifiable ROM called as EEPROM ROM can be repeatedly wiped and reprogrammed with the help of an using electrical voltage that is higher than usual. Unlike EPROM chips, EEPROMs can be changed without being taken out of the computer. However, an EEPROM chip must be completely deleted and reprogrammed, not just some part of it. Virtual memory, a memory management method that enables the use of secondary memory just like it was a component of main memory. In order to compensate for physical memory storage shortage, virtual memory uses hardware and software to temporarily shift data from RAM to disk storage. Next, we have memory versus storage. Although the term memory and storage are frequently used interchangeably, there are some distinct and important differences between both. Simply said, storage is secondary memory, while Memory is primary or main memory. Storage refers to where long-term data is stored, whereas memory refers to where short-term data is stored. On a computer, the term memory is most frequently used to describe the main storage, such as RAM. Information is also processed in memory with the help of RAM. Users have the potential to access data that is stored for a short time. As primary memory is volatile, meaning it is not retained when the computer is shut off, the data is only stored for a brief period of time. Data in a computer is stored in secondary memory, which is referred to as a storage. A hard drive, often known as hard disk drive, is an example of storage because storage is non-volatile. Data is not lost even after the computer is powered off and back on. For quick information retrieval, a running program may be in the main memory of the computer, but when the program is closed, it moves to secondary memory or storage. The amount of storage and memory space that is accessible differs as well. As compared to memory, a computer will often have greater storage capacity. For instance, a laptop may have 20 to 50 GB of storage space and 8 GB of RAM. The reason for the difference in space is that a computer will not need to quickly access all the data stored on it at once. Therefore, assigning about 8 GB of space will be plenty to run programs. Due to the inconsistent uses of these terminology in modern technology, memory and storage can be difficult to understand. For instance, flash memory is a sort of secondary storage, whereas RAM can be referred to as primary storage. It may be simpler in talk about memory in term of whether it is volatile or non-volatile, and storage in term of whether it is primary or secondary in order to avoid misunderstanding. Timeline of history and evolution of computer memory. Computer memory was first limited to a few bits of space in the early 1940s. The development of acoustic delay line memory was one of the more important indications of advancement at this period. Quartz crystals could be used as transducers to read and write bits, and delay lines could store bits in mercury as sound waves. A few 100,000 bits can be stored with the help of using this approach. Non-volatile memory was first studied in the late 1940s, and magnetic core memory, which allowed for memory recall in the absence of power, was developed. This technology has had advanced and become widely used in the 1950s, with help to bring about the creation of the PROM in 1956. Due to its extensive use, magnetic core memory predominated as the primary memory technology until the 1960s. In 1959, MOS semiconductor memory, also referred to as metal oxide semiconductor field effect transistors, was developed. As a result, MOS transistors can be used as component of memory cell storage. In comparison to magnetic core memory, MOS memory was less expensive and required less power. Beginning in the early 1960s, bipolar memory, that was bipolar transistors, were employed. Bob Norman was the first person that suggested the idea of using solid state memory on an integrated circuit for the first time in 1961. In 1965, IBM made a memory a common technology. On the other hand, when compared to the other memory types, user found solid state memory to be too expensive to use. Bipolar SRAM was created in the early to mid 1960s. Toshiba published DRAM in 1965 and SRAM was first used commercially in the same year. A MOS semiconductor device was used to manufacture ROM that was created in 1967. After the single transistor DRAM cells was created in 1966. N-type MOS, NMOS memory also began to gain popularity in the late 1960s and early 1970s. MOS-based memory began to be widely used as a form of memory in early 1970s. After 1 year, erasable PROM was introduced in the market and EEPROM was created in 1972. Next, we have register memory. Register memory is the smallest and fastest memory in the computer. It is not a part of the main memory and is located in the CPU in the form of registers, which are the smallest data holding elements. A register temporarily holds frequently used data, instructions, and memory address that are to be used by CPU. They hold instructions that are currently processed by the CPU. All data is required to pass through registers before it can be processed. So they are used by CPU to process the data entered by the user. Register hold a small amount of data around 32-bit to 64-bit. The speed of a CPU depend on the number of bits of registers that are built into the CPU. Registers can be different type based on their uses. Some of the widely used registers include accumulator or AC, data register or DR, and address register or AR. Program counter, PC, input output, address register, and many more. We have architecture of register memory. This architecture is driven by instructions through which operations are to be carried out on the registers and memory. The architecture is referred to as a register plus memory architecture. If all of the operands are contained in the register, an operation can have two operands. One of them can be in memory and the other one in a register. On the other hand, the both operands of operation are either in the register or in the memory, which distinguishes it from other architecture. Example of this memory are Intel x86 and IBM System 360. The number of registers in the CPU are fewer and they are also small in size. Its size is fewer than 64 bits. It is quicker as compared to disk memory and primary memory. The size of general purpose registers affects the word size. The computer provides instructions for the registration number and the register's address. Various register identifiers include R0, R1, R7, SP, and PC. A register server serves as a connection point between a program and the system data storage. Evolution of register memories include register memory is a fundamental component of modern computing, providing the fastest form of data storage within a central processing unit CPU. Registers serve as small high-speed data storage location directly accessible by the CPU, holding instructions, operands, and intermediate results for ongoing computations. The development of register memory has been pivotal in improving computational efficiency, enabling faster instruction execution and optimizing system performance. Origins and early concepts in 1940s and 1950s. The concept of registers emerged with the advent of the first electronic computers in the 1940s. Early computers such as ENIAC 1945 and EDAC 1949 utilized small specialized memory location within the CPU to store intermediate results of calculations. These early registers played a crucial role in executing arithmetic and logical operations efficiently. Another Newman architecture proposed by John von Neumann in the late 1940s formalized the use of registers as an internal part of computer control unit. The architecture introduced concepts such as a program counter PC, accumulator AC, and instruction registers IR, laying the foundation of modern register-based processing. Expansion and standardization, 1960s to 1970s. During the 1960s and 70s, computer architecture saw rapid advancements, leading to the standardized and expansion of register memory. Key development includes general purpose registers GPRs. Early CPUs has limited registers dedicated to specific tasks. The introduction of GPRS general purpose registers allowed for more flexible and efficient computations. Register-based addressing. The use of registers for direct memory addressing improved instruction execution speed. Pipelining processing. The emergence of instruction pipelining in architecture like the IBM System 360 leveraged registers to streamline computation. By the 1970s, most commercial processors incorporated a register file containing multiple GPRS general purpose registers, significantly enhancing processing capabilities. Integration in microprocessor during 1980s and 1990s. The transition to microprocessor in the 1980s marked a turning point in register memory uses. Notable advancements during this period includes larger register set. CPU like the Intel 8086 1978 introduces an extended set of registers, improving data handling. Floating point registers. The emergence of floating point coprocessors, example Intel 8087, provided dedicated registers for mathematical computations. Reduced instruction set computing, RISC. Reduced instruction set computing, RISC architecture, example ARM, MIPS, Power PCs emphasized using larger register files and reducing reliance on memory access. By 1990s, registers has become essential for optimizing instructions, execution speed, and minimizing memory bottleneck. Modern register architecture during 20s till present. In the 21st century, register memory has evolved to accommodate increasing computational demands. Key modern advancements include 64-bit registers. The shift from 32-bit to 64 architecture, example AMD 64, Intel x86 to 64 expanded registers width, enabling more efficient processing to large data sets. Vector and SIMD registers. Technologies like Intel SSE, AVX, and ARM Neon introduced specialized registers for parallel processing and multimedia applications. Register renaming and out of order execution. Modern CPUs employ registers remaining to optimize execution pipeline and prevent data hazards. AI and GPU register innovations. Graphic processing unit (GPUs) and AI accelerators utilize massive register files to handle parallel computational effectively. At last, we conclude by saying register memory has undergone significant evolution from its inception in early computation to its crucial role in modern processors. As computing technology continues to advance, innovations in the register architecture will remain essential for computing processing speed, improving energy efficiency, and enabling cutting edge application in artificial intelligence, gaming, and scientific computing. Next, we have types and functions of computer registries. The fetching, decoding, and execution operations are the three important roles that computer registers play. The register gathers and stores user-provided data instructions at the designated location. The instructions are deciphered and processed in order to provide the user with the desired output. To ensure that the user receives and understands the results as expected, the information must be thoroughly digested. The registers understand the task and store them in a computer memory. The same is provided to the user upon their request. Processing is carried out in accordance with user requirements. The computer system uses a variety of registers to store data and reduce memory utilization. Every register used by the CPU has a unique function. The sort of common registers are described below. Data registers. It is a 16-bit register which is used to store operands to be operated by the processor. It temporarily stores data which is being transmitted or received from a peripheral device. Program counter. It holds the address of the memory location of the next instruction, which is to be fetched after the current instruction is completed. So it is used to maintain the path of execution of different programs and thus executes the program one by one when the previous instructions get completed. Instructor register. It is a 16-bit register. It stores the instruction which is fetched from the main memory. So it is used to hold instruction code which are to be executed. The control unit takes instruction from the instructor register, then decodes and executes it. Accumulator register. It is a 16-bit register which is used to store the result produced by the system. For example, the results generated by CPU after the processing are stored in the AC register. Address registers. It is a 12-bit register that stores the address of a memory location where instructions or data is stored in the memory. Input-output address register. Its job is to specify the address of a particular input-output device. Input-output buffer register. Its job is to exchange the data between input-output module and the CPU. Next, use of register memory. The CPU may access frequently used data, instructions, and the addresses and the location of all these from the registers where needed. The register stores the instructions that the CPU will process. Prior to processing, every data must pass through the registers. Therefore, we can conclude that users enter data into registers to be processed by the CPU. The registers allow for the speedy acceptance, storage, and transmission of data. And any kind of register is utilized to carry out the precious tasks that the CPU requires. Users do not need to be very knowledgeable about the register because the CPU holds it as temporary memory and a data buffer. Registers acts as a buffers for copying data from main memory so that the processor can access it whenever it is needed. The data is kept in the registers so that the register is aware of the location and address and can use the information in order to determine the IP addresses. According to the requirement, the base register can modify computer operations on or operands and in computer system instructions. The address portion may be added to the register Each CPU has a few bytes allotted to the registers. The register contains fast memory and instructions to work on the system. Since the compiler stores temporary data in the register rather than the RAM, through which the program run more quickly than they should in the system. Next, why do we need register memory? CPU registers are very helpful for handling instructions quickly. It is at the top of the hierarchy of computer memory and is significantly faster as compared to other computer memory. Any type of small data, including registers, addresses, and instructions, can be stored there. These registers enable the CPU to function effectively and meaningfully. Next, we have difference between cache memory and register. Although they both generally store data, cache memory and registers differ greatly from one another. All of the devices frequently used data and instructions are stored in a cache memory. As a result, it accelerates the computer's overall performance and operation as well. The register, on the other hand, only stores a single item of information, such as a computer instruction or the location of a specific piece of data. Let's discuss the difference between register and cache memory. Below is the given table in which we are comparing the two terms on the basis of their unique characteristics to help make this topic more clear and more understandable. Parameters are definition, cache memory and register memory. In cache memory, in a computer system, the cache memory is the smallest and fastest part of the memory. In register, the register which make it up a minor portion of the computer CPU or quick sort storage component. Data storage in cache. Data storage, a computer cache stores the information and data that is recently used. In register, the register serves to store data that the computer CPU is currently processing. Cache used by CPU in order to find previously stored data. The CPU make use of cache memory. Used by CPU in register, registers are used by the CPU to process all the data and info that is needed. Location in cache. The cache of a computer can be found either inside the CPU or on the motherboard of the system. In register, the location are a component of a CPU of the computer device. In cache, data processing is to keep information in a process state. In register, it keeps information in an unprocessed state. CPU memory access speed. In cache, as compared to register memory, a system CPU can be access cache memory significantly more quickly. In register, a CPU can perform numerous operations on the contents of a register during a single clock cycle while working with registers. Example for caches are, example of cache memory includes database query, cache, dynamic page cache, and more. For registers, an instance of a register is a loop. Next, we have cache memory. Cache memory is high-speed memory which is small in size but faster than the main memory. The CPU can access it more quickly than the primary memory, so it is used to synchronize with high-speed CPU and to improve its performance. Cache memory can only be accessed by CPU. It can be a reserved part of the main memory or a storage device outside the CPU. It holds the data and program which are frequently used by the CPU. So it makes sure that the data is instantly available for CPU whenever the CPU needs this data. In other words, if CPU finds the required data or instruction in the cache memory, it does not need to access the primary memory, that is RAM. Thus, by acting as a buffer between RAM and CPU. It speeds up the system performance. Evolution of cache memory includes cache memory plays a crucial role in modern computing by bridging the speed gap between the central processing unit and the main memory. The development of cache memory has been driven by the need for faster and more efficient data retrieval. Over the decades, cache memory has evolved significantly from early conceptual implementation to sophisticated multi-level caching used in today's high-performance computing system. His generation was origins and early concepts during 1950s to 1960. The concept of cache memory emerged in the late 1950s and early 1960s when computer scientists realized that CPU were significantly faster than the available memory. This created a bottleneck as the CPU has to wait for data retrieval. Early computer designs relied on buffering techniques to temporarily store frequently accessed data, which laid the foundation of cache memory. IBM was one of the pioneers in cache memory implementation. The IBM 360 model 85, released in 1968, introduced a high-speed buffer memory that acted as an intermediate between the processor and RAM. This buffer was essentially the first cache, reducing the latency involved in the data accesses. The research during this period focuses on optimizing locality of reference, the principle that program tends to access a small portion of memory repeatedly. Formalization and commercial adoption, 1970s. During the 1970s, cache memory became more defined and structured. Researchers formalized the cache hierarchy, and computer architectures began incorporating small but high-speed memory units that stored frequently used data. Key development in this period includes introduction to associative caching. The concept of direct mapped, set associative and fully associative caches was developed to optimize data retrieval strategies. Implementation in commercial systems. Companies like Digital Equipments Corporation DEC and Intel integrated cache memory into their processor to improve computing speeds, write through and write back policies. This technique were introduced to maintain data consistency between cache and main memory. By the end of 1970s, cache memory has become a crucial component in many commercial computers, significantly improving computational performance. Integration on-chip cache during 1980s. In 1980s marked the significant leap in cache memory design with the introduction of on-chip cache in microprocessor. Previously, cache memory was separate from the CPU and required additional components, leading to increased manufacturing cost and slower communication. Key advancement during these decades, Intel 8486 1989, one of the first processor to integrate level 1 L1 cache directly on the CPU chips, reducing access time. Cache coherency protocols. With the rise of multiprocessor systems, protocols like MESI, modified exclusive shared invalid, were developed to maintain cache consistency. Increase in cache size. Cache size grew from kilobytes KB to megabytes, improving performance in computing tasks. Next, multi-level cache architecture during 1990s. In 1990s, saw the introduction of multi-level caching, significantly enhancing CPU performance. L1 and L2 cache implementation. Processor now featured a small but fast L1 cache and a larger L2 cache. that was either integrated within the CPU or placed externally. Pentium Pro 1995. Intel Pentium Pro 9 introduced an on-package L2 cache, making data access even faster. Branch prediction and prefetching. Advanced algorithm allowed cache to predict and prefetch data, reducing delays. L3 cache introduction. High-end servers and enterprise systems began using L3 cache to improve performance further. By the late 90s, cache memory has become a standard component in microprocessor, leading to substantial performance improvement in personal and enterprise computing. Multi-core processor and smart cache during 2000s. As computing demands increased, the 2000s saw the rise of multi-core processor, which required innovating caching technique. Key developments: shared versus dedicated cache. Some processors have dedicated cache per core, while others used a shared L3 cache for efficient data accesses. Intel Smart Cache 2006. Intel introduced Smart Cache where multiple cores shared the L2 or L3 cache dynamically. AMD's multi-level caching strategy. AMD implemented its own cache strategy to optimize performance in multi-core architectures. Increase in cache size. Cache size grow significantly with L2 and L3 caches reaching multiple megabytes. These improvements allow multi-core processors to handle intensive computing tasks more efficiently, enhancing gaming, software development, and scientific computing. Modern cache architectures, 20s, 10s to till present. Modern processors continues to refine cache memory strategies to maximize speed and efficiency. Recent advancement includes higher level caching. Some high-end processor now features L4 cache used mainly in GPU and high-performance computing systems. Adaptive cache allocation. Intel's cache allocation technology CAT optimizes cache uses dynamically based on workload demand. Infinity Cache. AMD's 20s. AMD introduced Infinity Cache and high bandwidth cache system used in GPUs to boost graphics processing speed. AI and machine learning optimization. Modern cache designs are optimized for AI workloads, reducing data movement latencies. Reduce latency with 3D stacking. Technologies like Intel Forus and AMD's vCache use 3D stacking to increase cache capacity without increasing chip size significantly. The evolution of cache memory has been a key factor in the advancement of computing performance. From the early buffering technique in the 1950s to today's multi-level AI optimization cache architecture, cache memory has continuously adapted to meet demands of faster and more efficient computing. As technology process, innovation in cache memory while continue to play a crucial role in shaping the future of computing, particularly in areas like artificial intelligence, cloud computing, and high performance computing. Type of cache memory includes L1. It is the first level of cache memory, which is called level 1 cache or L1 cache. In this type of cache memory, a small amount of memory is present inside the CPU itself. If a CPU has 4 cores, quad-core CPU, then each core will have its own level 1 cache. As this memory is present in the CPU, it can work at the same speed as of the CPU. The size of this memory ranges from 2 KB to 64 KB. The L1 cache further has two types of caches. Instruction cache, which stores instructions required by the CPU, and the data cache that stores the data required by the CPU. Next is L2. This cache is known as level 2 cache or L2 cache. This level 2 cache may be inside the CPU or else outside the CPU. All the cores of the CPU can have their own separate level 2 cache, or they can share one L2 cache among themselves. In case it is outside the CPU, it is connected with the CPU with a high speed bus. The memory size of this cache is in this range of 256 KB to the 512 KB. In terms of speed, they are slower than the L1 cache. Next is L3. It is known as level 3 cache or L3 cache. This cache is not present in all the processors. Some high-end processor may have this type of cache. This cache is used to enhance the performance of level 1 and level 2 cache. It is located outside the CPU and is shared by all the cores of the CPU. Its memory size range from 1 megabytes to 8 megabytes, although it is slower than L1 and L2 cache. It is faster than random access memory RAM. How does cache memory work with CPU? When CPU needs the data, first of all, it looks inside the L1 cache. If it does not find anything in L1, it looks inside the L2 cache. If again it does not find the data in L2 cache, it looks into the L3 cache. If data is found in the cache memory, then it is known as cache hit. On the contrary, if data is not found inside the cache, it is called a cache miss. If data is not available in any of the cache memories, it looks inside the random access memory, that is RAM. If RAM also does not have the data, then it will get the data from the hard disk drive. So when the computer is started for the first time or the application is opened for the first time, data is not available in cache memory or in RAM. In this case, the CPU gets the data directly from the hard disk drive. Thereafter, when you start your computer or open an application, CPU can get the data from the cache memory or RAM. Next we have the use of cache memory in computing. Cache memory is an essential component of modern computing, significantly enhancing the speed and efficiency of data processing. It serves as an intermediary between the CPU and main memory, that is RAM, storing frequently accessed data to reduce latency and improve performance. Without cache memory, processors would spend excessive time retrieving data from slower storage, leading to the performance bottlenecks. This essay explores the various uses of cache memory in computing and how it contributes to system efficiency, enhancing processor performance. One of the primary uses of cache memory is to enhance processor performance. CPUs operate at extremely high speed, whereas traditionally RAM is relatively slower. By keeping frequently used data close to the processor, cache memory minimizes the time taken to access information, thereby reducing memory latency. Instruction caching. Modern processors utilize instruction cache to store frequently executed instructions, improving execution speed. Data caching. Frequently used data is stored in data cache, reducing delays in fetching operands from RAM. Branch prediction and prefetching. Advanced CPUs use cache memory to predict and prefetch data and instructions, further optimizing performance. Multi-level cache system. Modern computing devices utilize a multi-level cache system, which consists of different layers of cache memory. Level 1, L1 cache, the fastest and smallest cache, located directly on the CPU core. L2, level 2 cache, larger but slightly slower than L1. used to store additional instructions and data. L3, level 3 cache, a shared cache among multiple CPU cores, enhancing multi-threaded processing. This hierarchical caching system ensures a balance between speed, capacity, and efficiency, optimizing overall system performance. Role in multi-core and parallel processing. Cache memory plays a crucial role in multi-core and parallel processing environments. As modern CPU integrate multiple cores, efficient caching strategies ensure smooth data sharing and synchronization. Shared versus dedicated cache. Some processors assign dedicated L1 and L2 cache to each core, while others use a shared L3 cache for inter-core communication. Cache coherent mechanism. Technologies like MESI, modified exclusive shared invalid protocol, maintain consistency between cache in multi-core systems. Hyperthreading and virtual caching. In processor with hyperthreading cache, memory optimizes the execution of simple threads by reducing redundant data fetches. Impact on operating system and software applications. Operating system and software applications rely on cache memory to improve execution speed and efficiency. Key areas where cache is extensively used include operating system caching. OS kernel use caching technique to store frequently accessed system calls and processes, reducing load times. Web browser caching. Web browser cache frequently visited websites, images, and scripts to reduce loading time and bandwidth uses. Database caching. Database use caching to store query results, reducing access time for repeated queries and improving responsiveness in high traffic applications. Virtual memory and page caching. Operating system memory management utilizes caching to optimize access to virtual memory, improving system responsiveness. Use in specialized computing application. Beyond general computing, cache memory plays a vital role in specialized fields such as gaming, artificial intelligence, and cloud computing. Gaming, high performance gaming CPUs and GPUs utilize cache memory to store frequently used textures, shaders, and physical calculations, reducing rendering lag. Artificial intelligence and machine learning. AI accelerates and deep learning models rely on cache memory to quickly access large data sets, enhancing processing efficiency. Cloud computing and distributed system. Cloud service provides use cache memory to optimize data retrieval and reduce latency in data centers. Energy efficiency and power consumption. Another critical use of cache memory is in optimizing energy efficiency and reducing power consumption. By minimizing data transfers between the CPU and the main memory, cache memory reduces power uses in battery powered devices such as smartphones and laptops, enhances overall thermal efficiency, preventing excessive heat generation in high performance processors, supports dynamic cache management, adjusting cache utilization based on workload demand to optimize power consumption. Cache memory is an indispensable component of modern computing, playing a crucial role in enhancing processor speed, optimizing multi-core processing, and improving software performance. Its application extends beyond traditional computing, influencing gaming, AI cloud computing, and energy efficient designs. As computing technology advances, cache memory will continue to evolve, ensuring faster and more efficient data processing for future generation of devices. Primary memory. Primary memory, also known as main memory or volatile memory, is a fundamental component of modern computing. It serves as the workspace where the computer stores data and instructions that the CPU actively processes. Unlike secondary storage, which retains data permanently, primary memory provides temporary storage and enables rapid access and execution of programs. This explores the uses, types, and significance of primary memory in computing. Types of primary memory are: primary memory is broadly categorized into two types: random access memory, RAM. This includes dynamic RAM and static RAM, which temporarily store data and program instruction for quick retrieval. Read-only memory ROM, a non-volatile memory type that contains firmware or essential system instructions such as the BIOS, ensuring the system can boot correctly. Enhancing system performance. The primary function of primary memory is to facilitate fast data access, significantly impacting system performance. Temporary storage. RAM holds active programs and data, allowing the CPU to retrieve information rapidly. Multitasking support. More RAM enables better handling of multiple applications simultaneously. Reduce dependency on secondary storage. Faster memory access minimizes delays caused by retrieving data from slower storage devices like hard drives. Next, we have role in operating system and applications. Operating systems and application heavily depends on primary memory for efficient execution. Memory management. The operating system allocate and deallocate memory dynamically to optimize performance. Virtual memory support. When RAM is insufficient, the system uses virtual memory swap space to extend its capability. Application execution. Software application load into RAM, ensuring smooth and responsive user interactions. Next, we have impact of specialized computing field. Primary memory plays a crucial role in advanced computing applications, gaming and graphics processing. High performance RAM ensures faster rendering and seamless gameplay. Artificial intelligence and machine learning. Large memory capacities enhance data processing for deep learning models. Cloud computing and virtualization. Cloud serves relay on extensive RAM for efficient data handling and virtual machine operations. Next, we have energy efficiency and technological advances. Modern computer demands energy efficient memory solutions. Low power DRAM used in mobile devices to extended battery life. High bandwidth memory enhances data transfer speed in high performance computing. Non-volatile RAM combines speed with data persistence for next generation computing. Primary memory is the cornerstone to modern computing, ensuring efficient data processing, seamless application execution, and improved system responsiveness. As technology advances, innovation in memory architecture will continue to shape the future of computing, enhancing performance, energy efficiency, and overall user experiences. Next, we have primary memory is of two types, RAM and ROM. RAM, volatile memory. It means it does not store data or instructions permanently. When you switch on the computer, the data and instruction from the hard disk are stored in RAM. CPU utilizes this data to perform a required task. As soon as you shut down the computer, the RAM loses all the data. ROM, non-volatile memory. It means it does not lose its data or program that are written on it at the time of manufacture. So it is a permanent memory that contains all important data and instructions needed to perform important tasks like the boot process. RAM, random access memory. RAM, which stands for Random Access Memory, is a hardware device generally located on the motherboard of a computer and acts as an internal memory for the CPU. It allows CPU to store data, program results. When you switch on the computer, it is the read and write memory of a computer, which means the information can be written to it as well as read from it. RAM is a volatile memory, which means it does not store data or instructions permanently. When you switch on the computer, the data and instructions from the hard disk are stored in the RAM. Example, when the computer is rebooted and when you open a program, the operating system and the program are loaded into RAM, generally from an HDD or SSD. CPU utilizes this data to perform the required task. As soon as you shut down the computer, the RAM loses the data. So the data remains in the RAM as long as the computer is on and lost when the computer is turned off. The benefit of loading data into RAM is that reading data from RAM is much faster than reading from the hard drive. In simple words, you can say that RAM is like a person, short term memory, and hard drive storage is like a person's long term memory. Short term memory remembers the things for a short duration, whereas long term memory remembers for a long duration. Short term memory can be refreshed with information stored in the brains. Long term memory. A computer also works like this. When the RAM fills up, the processor goes to the hard disk to overlay the old data in RAM with new data. It is like a reusable scratch paper on which you can write notes, numbers, etc. with a pencil. If you run out of space on the paper, you may erase what you no longer need. RAM also behaves like this. The unnecessary data on the RAM is deleted when it fills up and it is replaced with new data from the hard disk which is required for the current operations. RAM comes in the form of a chip that is individually mounted on the motherboard or in the form of several chips on a small board connected to the motherboard. It is the main memory of a computer. It is faster to write to and read from as compared to other memories such as hard disk, HDD, solid state drives, SSD, optical drive, etc. A computer performance mainly depends on the size or storage capacity of the RAM. If it does not have sufficient RAM, random access memory, to run the operating system and software program, it will result in slower performance. So, the more RAM a computer has, the faster it will work. Information stored in RAM is accessed randomly, not in a sequence as on a CD or hard drive. So, its access time is much faster. Next, we have functions of RAM. RAM has no potential for storing permanent data due to its volatility. A hard drive can be compared to a person's long term memory and RAM to a short term memory. Short term memory can only hold a limited number of facts in memory at any given time. However, it concentrates on immediate tasks. Facts kept in the brain, long term memory, can be used to replenish short term memory when it becomes full. This is also how computers operate when RAM is full. The CPU of a computer must constantly access the hard drive to overwrite the old data in RAM with the fresh data. The computer performance is slowed by this process. RAM will not run out of memory, unlike a hard disk of a computer, which can only hold so much data before it becomes completely full. However, the RAM and storage memory can both run out of space. How does RAM work? The term random access comes from that fact that any storage location which is used to describe RAM is something referred to as any memory address that can be directly accessed. Typically, random access memory was initially used to describe offline memory as opposed to ordinary core memory. In most cases, the term offline memory referred to magnetic tape, from which a particular piece of data can only be accessed with the help of finding the address sequentially. Beginning at the tape startings, data may be saved and retrieved directly to and from specified location thanks to the organization and control of RAM. Even while these other strong media, including the hard drive and CD-ROM, are accessed both directly and randomly as well. The word random access is not used to describe them. RAM is much like a collection of boxes, where each box can store either a 0 or 1. You may find the specific address for each box by numbering up the rows and down the column. An array is a collection of RAM boxes, and a cell is a single RAM box in an array. The RAM controller transfers the column and row address down a thin electrical wire attached into the chip in order to locate a particular cell. In a RAM array, each row and column contain its own address line. Any read data flow back on the different data line. RAM is contained in microchips and is physically small. Additionally, it has a limit. Additionally, it has a limited storage capacity for holding data. A typical laptop computer may have 8 GB of RAM, whereas a hard disk can store 10 terabytes. On the other hand, a hard disk drive holds data on magnetically coated surface, which looks like a Winley record. In contrast, an SSD holds data in memory chips that are non-volatile. Unlike random access memory, they don't require continuous power and will not lose information if the power is switched off. RAM microchips are collected simultaneously into memory modes. These slide into motherboard slot in computers. The motherboard slots and the processor are connected via a bus, which is a network of electrical pathway. Users can often add RAM modules up to a specific amount of PCs. A computer with more RAM uses less of the processor time reading information from the hard disk, which is slower as compared to reading information from RAM. Storage memory access time is measured in milliseconds, whereas RAM access time is measured in nanoseconds. How much RAM do you need? What the user is doing on the system determine how much RAM is required. For example, a system should have at least 16 GB of RAM, while more is preferred for editing videos. Also, Adobe advises a system should have at least 3 GB of RAM in order to run Photoshop CC on a Mac for photo editing. However, in 8 GB of RAM can slow things down if the user is simultaneously using other apps. History of RAM. The first time of RAM was introduced in 1947 with the William tube. It was used in CRT, cathode ray tube, and the data was stored as electrically charged spot on the face. The second type of RAM was magnetic core memory, invented in 1947. It was made up of tiny metal rings and wire connecting to each ring. A ring stored 1 bit of data and it can be accessed at any time. The RAM, which we know today as solid state memory, was invented by Robert Dennard in 1968 at IBM's Thomas J. Watson Research Center. It is specially known as dynamic random access memory and has transistor to store bits of data. A constant supply of power was required to maintain the state of each transistor. In October 1969, Intel introduced its first DRAM, the Intel 1103. It was its first commercial available DRAM. In 1993, Samsung introduced the KM48SL2000 synchronous DRAM, SDRAM. In 1996, DDR SDRAM was commercially available. In 1999, RDRAM was available for computers. In 2003, DDR2 DRAM began being sold. In June 2007, DDR3 SDRAM started being sold. In September 2014, DDR4 became available in the market. Types of RAM. There are integrated RAM chips can be of two types, static RAM and dynamic RAM. Both the types of RAM are volatile as both lose their content when the power is turned off. Static RAM. Static RAM is a type of random access memory that retains in state of data bit or hold data as long as it receives the power. It is made up of memory cells and is called a static RAM as it does not need to be refreshed on a regular basis because it does not need the power to prevent leakage. Unlike dynamic RAM, so it is faster than DRAM. It has a special arrangement of transistors that makes a flip-flop a type of memory cell. One memory cell stores one bit of data. Most of the modern SRAM memory cells are made of 6 CMOS transistors but lack capacitors. The access time in SRAM chips can be as low as 10 nanoseconds, whereas the access time in DRAM usually remains above 50 nanoseconds. Furthermore, its cycle time is much shorter than that of DRAM as it does not pause between accesses. Due to these advantages associated with the use of SRAM, it is primarily used for system cache memory. The high-speed registers and small memory banks such as a frame, buffer or graphic card. A static RAM is fast because the 6 transistors configuration of its circuit maintain the flow of current in one direction or the other, that is 0 or 1. The 0 or 1 state can be written and read instantly without waiting for the capacitor to fill up or drain. The early asynchronous static RAM chips performed read and write operations sequentially, but the modern synchronized static RAM chips overlap read and write operations. The drawback with static RAM is that its memory cells occupy more space on a chip than the DRAM memory cells for the same amount of storage space or memory as it has more parts than a DRAM, so it offers less memory chips. Next we have dynamic RAM, DRAM. Is DRAM dynamic RAM is also made up of memory cells. It is an integrated circuit made up of millions of transistors and capacitors which are extremely small in size and each transistor is lined up with a capacitor to create a very compact memory cell so that millions of them can fit on a single memory chip. So, a memory cell of a DRAM has one transistor and one capacitor, and each cell represents or stores a single bit of data in its capacitor within an integrated circuit. The capacitor holds this bit of information or data either as 0 or as 1. The transistor, which is also present in the cell, acts as a switch that allows the electric current circuit on the memory chip to read the capacitor and change its state. The capacitor need to be refreshed after regular intervals to maintain the charge in the capacitor. This is the reason it is called dynamic RAM, as it needs to be refreshed continuously to maintain its data or it would forget what it is holding. This is achieved by placing the memory on a refresh circuit that rewrites the data several hundred times per second. The access time in DRAM is around 60 nanoseconds. We can say that a capacitor is like a box that stores electrons. To store a 1 in the memory cell, the box is filled with electrons, whereas to store a 0, it is emptied. The drawback is that the box has a leak. In just a few milliseconds, the full box becomes empty. So, to make dynamic RAM work, the computer or memory controller has to recharge all the capacitors before they discharge. To achieve this, the memory controller reads the memory and then writes it right back. This is called refreshing the memory, and this process continues automatically thousands of times per second. So this type of RAM needs to be dynamically refreshed at all the times. Types of DRAMs are asynchronous DRAM. This type of DRAM is not synchronized with CPU with the CPU clock. So the drawback with this RAM is that CPU could not know the exact timing at which the data would be available from the RAM on the input-output bus. The limitation was overcome by the next generation of RAM, which is known as a synchronous DRAM. Synchronous DRAM. Synchronous DRAM began to appear in late 1996. In SDRAM, the RAM was synchronized with a CPU clock. It allowed the CPU or to be precise the memory control to know the exact clock cycle or timing or the number of cycles after which the data will be available on the bus. So the CPU does not need for the memory accesses, and thus the memory read and write speed can be increased. The SDRAM is also known as a single data rate SDRAM, SDR, SDRAM, as data is transferred only at each rising edge of the clock cycle. See the image in the following description. DDRAM, the next generation of asynchronous DRAM is known as DDR RAM. It was developed to overcome the limitation of SDRAM and was used in PC memory at the beginning of the year 2000. In DDR, SDRAM, DDR RAM, the data is transferred twice during each clock cycle, during the positive edge and the negative edge of a cycle. So it is known as double data rate SDRAM. There are different generations of DDR SDRAM, which include DDR1, DDR2, DDR3, and DDR4. Today, the memory that we use inside the laptop, desktop, mobile, etc., is mostly either DDR3 or DDR4 RAM. Types of DDR SDRAMs are DDR1 SDRAM. DDR1 SDRAM is first advanced version of SDRAM. In this RAM, the voltage was reduced from 3.3 V volt to 2.5 volt. The data transferred during both the rising as well as the falling edge of the clock cycle. So, in each clock cycle, instead of 1 bit, 2 bit are being prefetched, which is commonly known as 2-bit prefetch. It is mostly operated in the range of 133 MHz to 200 MHz. Furthermore, the data rate at the input-output bus is double the clock frequency because the data is transferred during both the rising as well as falling edge. So, if a DDR1 RAM is operating in 133 MHz, the data rate would be double 266 mega transfer per second. Next we have DDR2 SDRAM. It is the advanced version of DDR1. It operates at 1.8 volt instead of 2.5 volt. Its data rate is double the data rate of the previous generation due to the increase in the number of bits that are prefetched during each cycle. 4 bits are prefetched instead of 2 bit. The internal bus width of this RAM has been doubled. For example, if the input-output bus is 64-bit wide, the internal bus width of it will be equal to 128-bit. So a single cycle can handle double the amount of data. DDR3 SDRAM. In this version, the voltage is further reduced from 1.8 volt to 1.5 volt. The data rate has been doubled than the previous generation RAM as the number of bits that are prefetched has been increased from 4 bits to 8 bits. We can say that the internal data buses with the RAM has been increased 2 times than that of the last generation. DDR4 SDRAM. In this version, the operating voltage is further reduced from 1.5 volt to 1.2 volt, but the number of bit that can be prefetched is same as the previous generation. 8 bits per cycle. The internal clock frequency of a RAM is double of the previous version. If you are operating at 400 MHz, the clock frequency of the input-output bus would be 4 times. 1600 MHz and the transfer rate would be equal to 3200 mega transfer per seconds. Next, we have difference between static RAM and dynamic RAM. Static RAM and dynamic RAM. It is a static memory as it does not need to be refreshed repeatedly. It is a dynamic memory as it needs to be refreshed continuously or it loses the data. In static RAM, memory cell is made of 6 transistors, so its cell occupy more space on chip and offer less storage capacity than a DRAM of the same physical size. In DRAM, its memory cell is made of one transistor and one capacitor. So its cells occupy less space on a chip and provide more memory than a SRAM of the same physical size. SRAM is more expensive than DRAM and is located on processor or between a processor and main memory. DRAM is less expensive than SRAM and is mostly located on the motherboard. SRAM has a lower access time, example 10 nanoseconds, so it is faster than DRAM. And DRAM, it has a higher access time, example more than 50 nanoseconds, so it is slower than SRAM. SRAM stores information in a bistable latching circuitry. It requires regular power supply, so it consumes more power. DRAM, the information of each byte of data is stored in a separate capacitor within an integrated circuit, so it consumes less power. SRAM is faster than DRAM as its memory cells do not need to be refreshed and are always available. So it is mostly used in registers in the CPU and cache memory for various devices. In DRAM, it is not as fast as SRAM as its memory cells are refreshed continuously. But still, it is used in the motherboard because it is cheaper to manufacture and require less space. In SRAM, its cycle time is shorter as it does not need to be paused between access and refresher. In DRAM, its cycle time is more than the SRAM cycle. Example of SRAM are L2 and L3 LE cache in the CPU. Example of DDR3 and DDR4 in mobile phone computers, etc. In SRAM, size range from 1 MB to 16 MB. In DRAM, size range from 1 GB to 3 GB in smartphones and 4 GB to 16 GB in laptops. Next, we have RAM versus virtual memory. When the user executes several apps at once, a computer system can run sort on memory. Operating system can add virtual memory to make up for a lack of physical memory. Data is temporarily moved from RAM to disk storage in virtual memory and virtual address space in expanded utilizing active RAM memory and idle HDD memory to create continuous address that may carry a program and its data. Heavier program or many program running at once can be loaded onto a system with the help of using virtual memory. enabling each of the function as though it had infinite capacity without the need for the more RAM. Virtual memory has the potential to handle addresses twice as RAM can initially store at virtual location. A program's data and instructions are later converted to physical memory address at the time of execution. Virtual memory has a drawback in that it can make computers slower in performance as data must be translated between physical and virtual memory. Programs run straight from RAM when using only physical memory. RAM versus flash memory. The solid state chips are used to compromise both RAM and flash memory. However, due to variation in their design, performance requirement and price, they play distinct functions in computer system. When data is retrieved from storage, calculations are made in RAM, which is employed as active memory. Data must be deleted from NAND flash memory in entire blocks, which is a key distinction between flash memory and RAM. It is therefore slower as compared to RAM, where data can be deleted one bit at a time. However, NAND flash memory is non-volatile and less expensive as compared to RAM. It can save data even when the power is off. Unlike RAM, flash is frequently employed as the storage memory in SSDs, despite its slower speed, non-volatility, and lower price. RAM versus ROM. Computer memory that can only be read from, not written to, is known as read-only memory or ROM. When a computer is turned on, boot up programming from the ROM, it is used each time. In most cases, it cannot be reprogrammed or changed. The data in ROM is not lost when the power is cut off to the computer as it is non-volatile in nature. Consequently, read-only memory is employed to hold data permanently. On the other hand, random access memory is only able to store information monetarily, which means data is lost when the computer power is turned off. While RAM often have several gigabytes of storage, ROM typically have several megabytes. Trends and future direction. Non-volatile storage known as resistive random access memory RRAM and RERAM has the ability to change the resistance of the solid dielectric substance that it is made of. Devices that use RERAM has minimized whose resistance changes on the basis of the applied voltage. Oxygen vacancies, which are structural flaws in an oxide layer, are produced by RERAM. In a binary system, these vacancies represent two values like the electron and holes in a semiconductor. As compared to other non-volatile storage technologies like NAND flash, RERAM contains a faster switching rate. Additionally, it promises to use less power as compared to NAND flash and has a high storage density. Because of this, ReRAM is an excellent memory choice for sensors used in industrial, automotive, and Internet of Things application. In order to develop ReRAM technology and put chips into production, vendors have struggled for years. They are how being shipped by a few sellers. In the future, 3D X-point technology like Intel Optane may bridge the space between dynamic RAM and NAND flash memory. Selectors and memory cells exist at the intersection of perpendicular wires in the cross-point design of 3D X-points, which lacks transistors. Although 3dx point is non-volatile memory, it is slower as compared to DRAM. What should I look out for when buying RAM? The most recent DDR4 RAM generations operate at a frequency of about 2400 MHz. DDR4 memory that runs at about 3600 MHz and AMD processor and 32,000 megahertz for Intel processor is what gamer need. Hardcore gamers, professional programmers, and multimedia editors, among other users, could prefer higher clock memory for specialized suppliers like G-Skill or Corsairs, which has speed up to 4,800 megahertz. Aside from clock rate, latency, the interval of time between entering and executing a command in memory, is another important factor to consider when purchasing RAM. The performance increases with decreasing latency. You will require memory running at or above 4000 MHz and with a cache, column address sort or signal. Latency of 15 to 18 or less for high level performance. When you are going to purchase RAM, you might see this described as CL16, column latency 16. For instance, gamers should pay attention to this. Although regular users will not likely notice much of the difference. Additionally, if you are a Mac user and want to upgrade your RAM in your system, make sure you can do so before you start purchasing. Keep in mind the 32 window version. Finally, simply installing infinite amount of RAM into your computer system will not make it functional. Running a 64-bit version of Windows is required to use more than 4 GB of RAM in your system. 32-bit version have only the potential to use 3.5 GB. If you are a user of a 32-bit edition of Windows 7, you are required to update from the 32-bit version of Windows 7 to the 64-bit version to use 4 GB RAM of or more. However, keep in mind what if you have an old system and are installed a 64-bit version of Windows on this PC? It may have a negative impact. Windows addresses are now 64-bit long instead of simply 32-bit. This results in each application having a bigger memory footprint. The amount of RAM used by Windows 64-bit may increase by 20 to 50% on the basis of application you use. Therefore, using a 64-bit version only makes sense if your system has more money. Get more RAM the easy way. If you are upgrading or manually cleaning your RAM, it can be a hassle. A unique technology called sleep mode is available that identifies the shutdown resource fogging applications when they are not in use, which helps to improve the performance of the system. For example, you can download a free antivirus program such as Avast Cleanup and look for background and startup programs. You will notice performance benefits as soon as you put the program you don't actively need to use to sleep. Next, we have what is ROM. ROM stands for read-only memory. It is a memory device or storage medium that stores information permanently. It is also the primary memory unit of a computer and along with the random access memory RAM. It is called read-only memory as we can only read the programs and data stored on it, but cannot write on it. It is restricted to reading words that are permanently stored within the unit. The manufacturers of ROM fills the programs into the ROM at the time of manufacturing the ROM. After this, the content of ROM can't be altered, which means you can't reprogram, rewrite, or erase its content later. However, there are some type of ROM where you can modify the data. ROM contains special internal electronic fuzzes that can be programmed for a specific interconnection pattern or information. The binary information stored in the chip is specified by the designer and then embedded in the unit at the time of manufacturing to form the required interconnection pattern or information. Once the pattern or information is established, it stays within the unit even when the power is turned off. So, it is a non-volatile memory as it holds the information when even the power is turned off or you shut down your computer. The information is added to a RAM in the form of bits by a process known as programming the ROM, as bits are stored in the hardware configuration of the device. So ROM is programmable logical device PLD. A simple example of ROM is the cartridge used in video game consoles that allows the system to run many games. The data, which is stored permanently on personal computer and other electronic devices like smartphones, tablets, TV, AC, etc., is also known as example of ROM. For example, when you start your computer, the screen does not appear instantly. It takes time to appear as there are startup instructions stored in the ROM, which are required to start the computer during the booting process. The work of the booting process is to start the computer. It loads the operating system into a main memory RAM installed on your computer. The BIOS program, which is also present in the computer memory ROM, is used by microprocessor of the computer to start the computer during the booting process. It allows you to open the computer and connects the computer with the operating system. ROM is also used to store firmware, which is a software program which remains attached to the hardware or programmed on a hardware device like a keyboard, hard drive, video card, etc. It is stored in a flash ROM of a hard-based hardware device. It provides instructions to the device to communicate the instruction with other devices. Next, we have block diagram of ROM. The block of a ROM has n input lines and m output lines. Each bit contains of the input variable, which is known as address. Each bit combination that comes out through output lines is called a word. The number of bits per word is equal to the number of output lines, that is m. The address of a binary number refers to one of the addresses of n variable. So the number of possible addresses with n input variables is 2n. An output word has a unique address, and as there are 2n distinct addresses in a row, there are 2n separate words in the row. The word on the output line at the given time depends on the address value applied to the input lines. Internal structure of ROM. The internal structure comprises two basic components, decoder or OR gate. A decoder is a circuit that decodes and encodes date form, such as binary coded decimal (BCD) to a decimal form. So the input is in binary form and the output is its decimal equivalent. All the OR gates present in the row will have output of the decoder as their outputs. Let us take example of 64 into 4 row. The structure is known for the read-only memory consists of 64 words of 4-bit each. So there would be 4 output lines and one of the 64 words available on the output lines is determined for the 6 input lines, as we have only 6 input because in the row we have 26 equals to 64. So we can specify 64 addresses or minute terms. For each address input, there is a unique selected word. For example, if the input address is 00000, the word 0 will be selected and applied to the output lines. If the input address is 11111, word number 63 is selected and applied to the output line. Next, we have features of ROM. ROM, read-only memory, possesses several distinct features that make it suitable for various applications. Let's explore some key features of ROM in simple language. Non-volatile memory. ROM is a non-volatile memory type, thus it keeps its data even when the power is switched off. This makes it suitable for storing permanent instructions and data since it guarantees that the recorded information will remain intact and may be accessed whenever necessary. Read-only nature. Reading-only memory or ROM, as its name implies, prevents data from being readily modified or built. These characteristics provide stability, and prevents accidental alternations, ensuring the integrity and reliability of the stored information. Next, we have permanent storage. ROM offers permanent storage of data and instructions. Once the data is programmed into ROM during manufacturing, it remains fixed and cannot be changed without physically replacing the ROM chip. This permanence guarantees the consistency and stability of the stored information. Firmware storage. ROM is commonly used for storing firmware containing essential instructions for operating electronic devices. ROM, non-volatile and read-only nature ensures that the firmware remains unchanged, providing reliable and consistent functionality to the device. Booting and initialization. ROM plays a crucial role in electronic systems, booting and initialization process. The firmware stored in ROM contains the initial instruction required to start the system, load the operating system, and initiate the hardware components. This ensures a smooth and controlled startup sequence for the device. Data security. ROM offers inherent data security. Since the data stored in ROM cannot be modified or erased, it protects against unauthorized alterations or tampering. This feature enhances the security and authenticity of the stored information, making ROM suitable for critical instructions and sensitive data. Instant read access. ROM provides instant read access to the stored instruction and data. The information can be accessed directly without time-consuming loading, enabling quick retrieval and execution of essential instruction. Compatibility. ROM is compatible with various systems and architectures, allowing seamless integration into different electronic devices and systems. This compatibility ensures that ROM can be utilized in various applications. Reliability. Due to its read-only nature, ROM offers high reliability. The data stored in ROM is not susceptible to accidental modifications or loss, ensuring consistent and predictable performance over time. Such dependability is crucial for important systems where stability, the data and data integrity are of the utmost importance. Cost efficient. ROM is generally more cost efficient than other memory types, making it an economical choice for many applications. Production costs are cheaper since the manufacturing producer procedures used to produce ROM as are well established. Types of ROM. Mass read-only memory. MRO. It is the oldest type of read-only memory. It has become obsolete, so it is not used anywhere in today's world. It is a hardware memory device in which program and instructions are stored at the time of manufacturing by the manufacturer. So it is programmed during the manufacturing process and can't be modified or reprogrammed or erased later. The MROM chips are made of integrated circuits. Chips send a current through a particular input-output pathway determined by the location of fuses among the rows and columns on the chip. The current has to pass along a fuse-enabled path, so it can return only via the output and manufacturer chooses. This is the reason the rewriting and any other modification is not possible in the memory. Programmable read-only memory. PROM is a blank version of ROM. It is manufactured as blank memory and programmed after manufacturing. We can say that it is kept blank at the time of manufacturing. You can purchase and then program it once using a special tool called a programmer. In the chip, the current travels through all possible pathways. The programmer can choose one particular path for the current by burning unwanted fuses by sending a high voltage through them. The user has an opportunity to program it or to add data and instructions as per his requirement. Due to this reason, it is also known as the user programmed ROM as a user can program it. To write data onto a PROM chip, a device called PROM programmer or PROM burner is used. The process of programming a PROM is known as burning the PROM. Once it is programmed, the data cannot be modified later. So it is also called as one-time programmable device. Uses it is used in cell phones, video game console, medical devices, RFID tags, and more. Erasable and programmable read-only memory. EPROM is a type of ROM that can be reprogrammed and erased many times. The method to erase the data is very difficult. It comes with a quartz window through which a specific frequency of ultraviolet rays light is passed for around 40 minutes to erase the data. So it retains its content until it is exposed to the ultraviolet light. You need a special device called a PROM programmer or PROM burner to reprogram the EPROM. Uses it is used in some microcontrollers to store program. Example, some version of Intel 8048 and Freescale 64HC11. Next, electrically erasable and programmable read-only memory, EEPROM. ROM is a type of read-only memory that can be erased and reprogrammed repeatedly up to 10,000 times. It is also known as flash EEPROM as it is similar to flash memory. It is erased and reprogrammed electrically without using ultraviolet light. Access time is between 45 to 200 nanoseconds. The data in the memory is written or erased one byte at a time, byte per time, whereas the flash memory data is written and erased in blocks. So it is faster than EEPROM. It is used to store a small amount of data in computer and electronic system and devices such as circuit boards. Uses the BIOS of computer is stored in the memory. Next we have flash memory. It is an advanced version of EPROM. It stores information in an arrangement of array of memory cells made from floating gate transistors. The advantage of using this memory is that you can delete or write blocks of data around 512 bits at a particular time. Whereas in EPROM, you can delete or write only one byte of data at a time. So this memory is faster than EEPROM. It can be reprogrammed without moving it from the computer. Its access time is very high, around 45 to 90 nanoseconds. It is also highly durable as it can bear high temperature and intense pressure. It is used for storage and transferring data between a personal computer and a digital devices. It is used in USB flash drives, MP3 players, digital cameras, modem, and solid state drives. The BIOS of many modern computers are stored on a flash memory. Next, we have uses of ROM. ROM, read-only memory, is used in various electronic devices. Let's explore the numerous ROM apps found in these electronic devices. First is computer. In computer system, ROM is essential, the basic input-output system, BIOS. And first startup instructions are stored as a part of computer firmware. The firmware included in ROM is in charge of initializing the hardware elements, running self-test, and loading the operating system into memory when you switch on your computer. Video games. ROM is widely used in video games. Game data was previously stored on ROM cartridge in earlier gaming consoles and portable devices. These cartridges carried the game's code, graphics, sound, and other components of ROM chips. A gaming console loads the game when you insert a game cartridge by reading the data from the ROM chip. Using ROM in video games allowed for easy distribution and ensured that the game data remained intact without the risk of accidental modification. Smartphones. ROM is essential in smartphones for storing firmware such as the operating system and built-in applications. To maintain consistency throughout the device existence, Manufacturers program the firmware into the ROM during the device construction. The bootloader, which starts the booting process and loads the operating system, is also included in ROM. By utilizing ROM, smartphones can provide stable and reliable performance and protect the firmware from potential corruption or tampering. Digital speed meter. In the automotive industry, ROM is used in digital speed meters or speedometers. The ROM chip in these devices stores the calibration data and conversion tables needed to measure the display the vehicle speed accurately. This ensures that the speed meter operates consistently and provides accurate reading. The non-volatile nature of ROM ensures that the calibration data remains intact, even if the power is disconnected or the vehicle is turned off. Programmable electronics. ROM is used in programmable electronic devices, microcontrollers, and programmable logic devices. Those devices frequently use programmable read-only memory or erasable programmable read-only memory. Users can program these ROM chips to preserve certain information or instructions that the device can access and carry out. This flexibility allows for customization and flexibility in various digital applications, along with robotics, automation, and control system. Next, we have advantages of ROM. First advantage is data retention. ROM maintains data even without power, ensuring that crucial data is retained and accessible whenever necessary. Permanent storage. ROM's non-modifiable nature assures that the information stored inside stays intact, making it a reliable and consistent source of data and instructions. Reliable performance. As ROM is read-only, unintentional modifications are prevented, ensuring that stored data will work reliably and consistently over time. Non-volatile memory. ROM is an option for storing important instructions, firmware, and data that shouldn't be changed since it can preserve data without a constant power source. Stability. The ROM offers a strong basis for the booting process and overall system function by storing crucial instructions and calibration data, assuring consistent and predictable performance. Data security. Read-only memory protects against unauthorized alterations, strengthening the security of data held within the preventing unauthorized access. Instant accessibility. The ability to instantly access data and instructions stored in ROM reduces the need for time-consuming data loading procedures, allowing for speedy system operations. Simple design and manufacturing. The design of ROM chips make it simple to integrate them into electrical equipments. Cost effectiveness. ROM is often less expensive than other memory types, making it a cost-effective option for many applications without compromising performance. Compatibility. ROM may easily be integrated into various electronic systems and devices since it is compatible with various architectures and systems. Next, we have disadvantages of ROM. Immutability. The main disadvantage of ROM is its inability to be modified or updated. Once data is programmed into ROM, it cannot be changed, limiting its flexibility and adaptability in certain applications. Limited flexibility. Unlike writable memory, such as RAM or flash memory, ROM does not allow for dynamic changes or updates to the stored data, restricting its use in situations that require frequent modifications. Manufacturing challenges. Manufacturing ROM chips requires special processes, making them less flexible and potential more expensive to produce than other types of memory. Design constraints. The fixed nature of ROM imposes design constraint as the data programmed into it cannot be easily altered or expanded. This can be limiting when system requirements change or additional functionality is desired. Time-consuming development. Creating a programming ROM requires significant time and effort during the development phase. which may slow down the overall product development cycle. Higher cost for small scale production. The initial cost associated with raw production, such as mass creation, can be relatively high, making it less cost effective for small scale or customized production runs. Lack of upgradability. ROM can only be upgraded or replaced with newer versions by physically replacing the entire chip, which can be costly and impractical in many situations. Storage inefficiency. ROM is read-only unused space within the ROM chips cannot be utilized, resulting in potential storage inefficiency. Limited error correction. Unlike other memory types, ROM does not provide built-in error correction mechanism, which can disadvantage application with critical data integrity. Reduced versatility. The fixed nature of ROM makes it less versatile for application that require dynamic storage and frequency changes to stored data. Next, we have secondary storage in which hard disks are considered. The secondary storage device which are built into the computer or connected to the computer are known as secondary memory of a computer. It is also known as external memory or auxiliary storage. The secondary memory is accessed indirectly via input-output operations. It is non-volatile, so permanently stores the data even when the computer is turned off or until this data is overwritten or deleted. The CPU can't directly access the secondary memory. First, the secondary memory data is transferred to primary memory, then the CPU can access it. Some of the secondary memory or storage devices are hard disk. It is a rigid magnetic disk that is used to store data. It permanently stores data and is located within a drive unit. The hard disk is also known as a hard drive. It is a rigid magnetic disk that stores data permanently, as it is a non-volatile storage device. The hard disk is located within a drive unit on the computer's motherboard and comprises one or more platters packed in an air-sealed casing. The data is written on the platter by moving a magnetic head over the platters as they spin. The data stored on computer hard drive generally includes the operating system, installed software, and the user's file and programs, including picture, music, videos, text, documents, etc. Components of hard drive are the main component of hard drive includes the head actuators, read-write actuators arm, read-write head, platter, and spindle. A circuit board, which is called the disk controller or interface board, is present on the back of a hard drive. It allows the hard drive to communicate with the computer. Next, we have solid state drive, SSD. Solid state drive is also a non-volatile storage medium that is used to hold and access data. Unlike a hard drive, it does not have moving components, so it offers many advantages over SSD, such as faster access time, noiseless operations, less power consumption, and more. As the cost of SSD has come down, it has become an ideal replacement for a standard hard drive in desktop and laptop computers. It is also suitable for notebooks and tablets that does not require lot of storage. Next, we have pen drives. Pen drive is a compact secondary storage device. It is also known as USB flash drive, thumb drive, or a jump drive. It connects to the computer via a USB port. It is commonly used to store and transfer data between computers. For example, you can write a report using a computer and then copy or transfer it in the pen drive. Later, you can connect this pen drive to a computer to see or edit your report. You can also store your important document and pictures, music, videos in a pen drive and keep it at a safe place. Pen drive does not have movable parts. It comprises an integrated circuit memory chip that stores the data. This chip is housed inside a plastic or aluminum casing. The data storage capacity of the pen drive generally ranges from 2 GB to 128 GB. Furthermore, it is a plug and play device as you don't need additional drivers, software and hardware to use it. Next, we have SD cards. SD cards stand for a secure digital card. It is often used in portable and mobile devices such as smartphones and digital cameras. You can remove it from your device and see the things stored in it using a computer with a card reader. These are many more memory chips inside the SD card that store the data. It does not have moving parts. SD cards are not created equal, so they may differ from each other in terms of speed, physical size, and capacity. For example, standard SD cards, mini SD cards, and micro SD cards. Next, we have compact disc. Compact disk is a portable secondary storage device in the shape of round medium disk. It is made up of polycarbonate plastics. The concept of CD was co-developed by Philips and Sony in 1982. The first CD was created on 17th August 1982 at a workshop of Philips in Germany. In the beginning, it was used for storing and playing sound recordings. Later, it was used for various purposes such as for storing documents, audio files, videos, and other data like software program in a CD. Physical characteristics of CD and structure of CD or structure of CD. A standard CD is around 5 inches in a diameter and 0.05 inches in thickness. It is made of a clear polycarbonate plastic substrate, a reflective metallic layer, and a clear coating of acrylic plastic. These thin circular layers are attached one on top of other as described. The polycarbonate disk layer at the bottom has the data encoded by creating lands and pits. The polycarbonate disk layer is coated with the thin aluminum layer that reflects the laser. The reflective aluminum layer is coated with the liquid layer to prevent oxidation in order to protect the below layers. It is generally spin coated directly on the top of the reflective layers. The label printed is applied on the liquid layer or network is screen printed on the top of the disk on the liquid layer by offset printing or screen printing. Next we have how does the CD work? The data or information is stored or recorded or encoded in CD digitally using a laser beam that etches tiny indentations or bumps on its surface. The bumps is called a pit, which represents the number 0. Space where the bumps is not created is called land and it's represent the number 1. Thus, the data is encoded into a compact disk by creating pits 0 and lands 1. The CD players use laser technology to read the optical recorded data. Next, we have DVD. DVD is a sort of digital versatile disc or digital video disc. It is a type of optical media used for storing optical data. Although it has the same size as a CD. Its storage capacity is much more than a CD. So it is widely used for storing and viewing movies and to distribute software programs as they are too large to fit on a CD. DVD was co-developed by Sony, Panasonic, Philips, and Toshiba in 1995. Types of DVDs can be divided into 3 main categories, which are as follow. DVD-RAW, read-only. These type of DVD come with media already recorded on them, such as movie DVDs. As the name suggested, data on these discs cannot be erased or added. So these discs are known as a read-only or non-writable DVDs. DVD are writable. It allows you to record or write information to the DVD. However, you can write information only once as it becomes a read-only DVD. once it is full. DVD-RW, writable and erasable. This type of disk can be erased, written, or recorded multiple. Next, we have memory units. A memory unit is a fundamental part of a computer machine that performs a vital functioning for storing and retrieving information and instructions. Memory units have distinct purposes, including primary and secondary memories. In this article, we will delve into the concept of memory units, their kinds, functions, and importance within the international field of computing. Memory units are the lifeblood of computer structures. They offer the potential to store and get proper entry to statics, instructions, and packages, enabling computer structures to carry out a large variety of obligations. In short, memory units are the digital brain of a PC or laptop, allowing it to systematize, hold, and consider facts as desired. They are vital for the functioning of every hardware and software component of computer system, making them a vital part of any computing devices. Importance of memory unit. Speed. Memory units make it possible to store and retrieve instructions and data quickly, which reduces processing instance and boosts overall system performance. This is crucial when handling huge amount of data or operating complicated programs. Temporary storage. Memory units serve as temporary storage for data and programs that are currently in use, allowing users to quickly move between programs and files without waiting for data to be loaded from a storage device. Multitasking. Memory units allow computer systems and different digital devices to do many tasks simultaneously because they can store and retrieve data for multiple programs simultaneously. Reliability. Memory devices are extremely reliable because they are made of resist normal wear and tear. They are a strong and reliable storage option because they are less vulnerable to damage from outside forces like shock or vibration. Accessibility. Memory units are readily available and can be quickly updated or changed. This makes increasing the system memory capacity simple, enabling users to manage more data and execute demanding programs. Energy efficiency. More units use less power than standard hard drives, resulting in lower heat generation and reduced cooling requirements. This makes them more energy efficient, specifically crucial for devices like smartphones and laptops with limited battery lives. Next, we have types of memory units. Different kinds of memory units are utilized in computers as each has its own purpose. Let's observe some common type. RAM, random access memory. RAM is like a quick and temporary workspace in your computer. It stores data and program that your computer is actively using. When you open a file or run a software, it gets loaded into RAM so your laptop can access it quickly. However, RAM is only sometimes permanent storage. So everything in RAM is lost when you switch off your computer. ROM, read-only memory. Read-only memory is a memory that stores essential records that your laptop needs to start up and run essential functions. It carries firmware or software programs. This is permanently programmed into a computer circuitry. The records in ROM cannot be modified, so it is secure and reliable. Cache memory. Cache memory is a volatile memory used to store data or often access instructions. Since the cache memory accesses data more quickly than RAM, this can enhance system performance. Data can be accessed more quickly thanks to the greater proximity of cache memory of the CPU. Virtual memory. Virtual memory is a method of increasing available memory by utilizing hard drive space. When RAM is in capacity, the computer temporarily transfers some data to the hard drive to make room in RAM for different programs. This method enhances computer performance when running numerous programs by allowing the machine to store more information than is feasible in RAM. Flash memory. Flash memory is a non-volatile memory frequently appearing in solid nation drives, USB drives, and memory cards. It is extra reliable and faster than traditional hard drives, making it appropriate for uses in devices that are portable. Transistor used in flash memory for data storage remain current even if the power has been switched off. Registers. Registers are quick, small memory units found on the CPU. They can temporarily store data during processing, like computation results or the content of creation of certain memory addresses. Although registers are the quickest type of memory currently accessing, their production costs are also higher. Next, we have functions of memory unit. Memory devices serve numerous critical features in a computer device, and those capabilities are essential for the overall operation and ordinary performance of the system. First is data storage. Memory device offers storage for both transient and long-term facts. The primary memory quickly holds statics and commands while they are being actively used by the CPU, ensuring that the computer can respond quickly to character input. Secondary memory serves as a long-term garage answer, permitting customer to preserve files, set up software, and keep statics that persist even after the computer is turned off. Data retrieval. Memory units allow the computer system to retrieve records and command rapidly. Primary memory is, in particular, designed for quick record retrieval, offering the CPU the essential source of execute applications and carry out obligations successfully. Data processing. The CPU uses number of memory as a workspace for information processing. It makes static and commands for secondary memory into number one memory for processing. Once processing is completed, the result may be stored or returned to the secondary memory, making an allowance for fact, modification, and garage. Multitasking. Memory units play an important role in multitasking. They permit the computer system to switch among distinctive packages and duties with the aid of storing and handling the fact and instructions for everyone. With enough number one memory, a computer can effortlessly cope with a multiple techniques simultaneously, enhancing productivity and customer enjoyment. Next, we have system performance. The amount and velocity of memory in a PC or laptop appreciably affect its ordinary performance. A computer system with larger primary memory can manage huge and more complex programs, leading to the higher performance and faster reaction between times. Additionally, the entire speed of memory device influences the PC processing velocity, as quicker memory allows faster information retrieval and execution of instructions. Next, we have measurement of memory units. Memory units are used to measure and represent data. These units, which can be measured in bit and bytes, offer a technique to estimate the volume of data which can be stored in a specific device or system. Some of the commonly used memory units are bit, binary digit, KB, kilobyte, MB, megabyte, GB, gigabyte, TB, terabyte, PB, petabyte, EB, exabyte, ZB, zettabyte, and YB, yottabyte. Bit. The computer memory unit start from bit. A bit is the smallest memory unit to measure data stored in main memory and storage devices. A bit can have only one bit value out of 0 and 1. Byte. It is the fundamental unit to measure data. It consists 8 bit or is equal to 8 bit. Thus, a byte can represent 2 into 8 or 256 values. They measure the size of the file, document, image, and other data types. Kilobyte. The kilobyte contains 1024 bits. It is a frequently used to indicate data storage ability and the dimension of small files. A small image or roughly 1024 character of text can be stored in 1 kilobyte. If frequently appears in the spreadsheet, text document, and small image files. Although greater unit of measurement have gained popularity as data files have grown in size, kilobytes are still in use today. Next, we have megabyte. A megabyte contains 1024 kilobytes. In comparison to kilobyte, it represents more data. Longer text pieces, high-resolution photos, and brief audio snippets can all fit into a megabyte. It is frequently used for calculating the size of the document, software package, and media files containing songs and short films. Even though bigger units of measurement is being used more often due to the expanding amount of data files, megabytes are still important and commonly used. Next, we have gigabyte. A gigabyte contains 1024 megabyte. It has a considerable quantity of data storing capacity. Larger files such as high dimension films, entire photo album, and software program can fit within a gigabyte. Hard drives, solid nation drives, and different types of data storage devices, storage capacities are regularly measured using this technique. Gigabytes are a common unit of measurement in recent times, particularly with the growth in the size of multimedia files and the demand of big amount of storage. Next, we have terabyte. A terabyte contains 1024 gigabytes. It represents a huge quantity of data storage capacity. Large databases, enormous video collection, and enterprise-level storage system may all store a lot of data in a terabyte. High capacity external hard drives, cloud storage services, and data centers frequently use it. Terabytes are becoming more and more significant as the need for large-scale data processing and storage increases. Petabyte. It represents the huge quantity of data storage capacity. Huge amount of data such as important video libraries, huge database, and enormous collection of high-resolution photographies can fit into a petabyte. It is frequently employed in data centers, cloud storage solution, and data-intensive scientific researches. Exabyte. EB and exabyte contains 1024 petabyte. It has a huge quantity of storage capacity of data. Large-scale data warehouse, worldwide internet traffic, and enormous video archives can be stored in exabytes. Large-scale scientific simulations, cloud computing infrastructure, and enterprise-level storage solutions all frequently rely on it. Zettabyte. A zettabyte is 1024 exabyte. It represents a data storing capacity that is nearly beyond imagination. Mind-boggling amount of data, such as global internet content, long-term archival storage, and through global data analysis, can be stored in zettabyte. Yottabyte, UIB. A yottabyte contains 1024 zettabyte. It represents an unbelievable volume of data storage. A yottabyte may store unimaginable amount of data, such as if equivalent to storage and internet content, may times over on tracking enormous amount of data for all available worldwide. In the area of computing, memory is the backbone of computer system, permitting record storage, retrieval processing, and multitasking. These are available critical types. Number one, memory, which is unstable and designed for instant information entry. And secondary memory, which is non-unstable and used for long-term information storage. Memory units are important for machine universal performance, statistical integrity, or client productivity, making them an important element in present day computing gadgets as generating advances. Memory devices keep adapting, providing greater ability and quicker speed to fulfill the demand of contemporary computing packages and customers. Thank you.